Apologies for the technical hiccup there, and I think I'm going to try and catch up a little on time. So I'm going to have a presentation, really a technical presentation about CobBauge, and then in 15 or 20 minutes pass you over to live to Plymouth University, where we'll have a demonstration of the practical side of the CobBauge project. So I'm going to canter through lots of slides which have graphs and technical stuff, and not necessarily expecting you to read all of these, but I'll explain the high points and the low points. And then, if you want to look at more detail, you can revisit the presentation later on at your leisure. So CobBauge then is an attempt at thermal and technical optimization of traditional cob construction. And the key thing here really is this phrase, optimization. How can we get the most out of cob construction for modern society? My name is Tom Morton from Earth Building UK and Ireland, one of the project partners, but I'm really part of a big team of universities and other organisations from the south of England and the north of France. And today I'm presenting a paper which is principally the work of François Streff of the Parc National Régional des Marais du Cotentin et du Bessin. And apologies for our French audience there. So I'm going to introduce how we're doing the project, present our laboratory and materials research to date, look at the construction technique and prototype phases, and outline our ongoing work that's in progress at the moment. So why optimize cob? For those who don't know, cob, or bauge as it's known in France, is a monolithic earth material formed of clay, earth and straw, which is built in lifts to form load-bearing walls, usually about 600 millimeters thick. It's a very traditional form of construction in these regions and is estimated to be at least 48,000 buildings equally shared between the south of the UK and the north of France. And the material is also being used for contemporary buildings. So why optimize cob? There's several reasons. First, cob fails to comply with modern building regulations in France and in the UK. In the UK, there's a minimum requirement U value of thermal insulation of 0.3 watts per meter squared degree Kelvin, and in France, it's 0.36. And these are values which are only going to become more stringent as time goes on. A traditional cob wall would typically have a U value of about 0.79. And to comply with regulations, you'd have to build a wall about 2 meters thick, which is neither practical nor economic. Or if you were to reduce the density to improve thermal resistivity, you would have to take the density down to 670 kilos per meter cubed, which isn't strong enough to support the weight of the building. So traditional cob doesn't really match what we're trying to get out in terms of a performance for modern buildings, at least by these parameters. In this image, and this goes back to some of the points Peter was making, this is a thermal image of a building that's got different kinds of construction from different periods. And the cob, the 300-year-old cob wall on the right, achieves a U value of about 0.5. So this is performance in a live building, as it were. Better than the stone wall that's dates from 100 years ago, and the brick cavity wall from the 1960s. And it's comparable with the insulated concrete block wall from the 1990s. But the point is that none of these meet current standards, and they're going to become less and less for future standards. And the second reason is to reduce carbon emissions. A concrete block wall is typically about 1,500 megajoules per meter squared. And a cob wall with lime renders is about 540 megajoules per meter squared. And if we use earth renders rather than limes, you can get that down to about 200 megajoules per meter square. So vastly lower carbon emissions than conventional construction techniques. And of course, you need to look at these things not only at the time of point of construction, but over the whole life cycle of the building material. And earth materials being infinitely recyclable obviously perform well there as well. And the other reasons then are a healthy indoor environment, the reduction of construction waste, reducing environmental pollution and resource depletion. and for reasons of cultural sustainability. But it has to be said, in terms of our project, the principal focus has been on the thermal and structural performance. So looking at the optimization of materials and our laboratory tests, we selected 6 soils from the south of England and 6 soils from the north of France, and we characterized these through a range of standard soil tests. This is the particle size distribution graph. Hold on. And this is a chart showing the activity level of the different types of clay. And then we also looked at 6 natural fibres which are available in the bioregion, these being reed, hemp straw, wheat straw, flax shiv, and hemp shiv. And we characterised these for water absorption and for tensile strength. And then we looked at many possible mixtures, varying the soil type, fibres, water content, and the amount of fire, and we narrowed it down to a selection for further testing. The parameter for the load-bearing cob were fibre content between 2.5% and 5%, water content to get a plastic mix, soil type, and fibre type. And this is the range of tests we did for the cob. We made samples, and we tested them for compressive strength, and a range of results emerged, mainly characterised by the fibre content. In the light earth mixtures, we varied the fibre content between 35 to 50%. We used the water as a slip, and we used 3 soils, primarily hemp shiv. And these are the chart of the tests we did. We made samples and we tested them for thermal flow, characterising the results in a distribution graph, and fair to say most of them achieved a satisfactory result. So we investigated how we could design a mix with these materials that could achieve a good thermal performance and a good structural performance. At a density of 920 kilograms per meter cube, we're not achieving sufficient strength to hold up the weight of the building, and yet it still hasn't got a U value below 0.41, remembering that 0.3 is the current regulatory standard. So we couldn't design a material that satisfied both criteria. And this took us to the conclusion that we needed a composite material of 2 layers, one with a dense material to take the structural load and the other a light material to provide thermal performance. We looked at mixes of composites of 2 layers, here varying the thickness and the density of the lightweight cob to fine-tune the result down to the 0.3 U value within a 500 mil wall. And here we're looking at the amount of fibre in the load-bearing cob and how this affects the density. So the optimal mix was a wall of 550 millimeters thick with a dense cob layer at 1500 kilos per cubic meter and light cob at 340 kilos per cubic meter, achieving a U value of 0.27. And we looked at whether the dense cob should be on the inside and the lightweight on the outside, or the other way around, and how each affected the thermal and the moisture performance. And we concluded that the insulating light cob should be on the outside and the dense cob would be better on the inside. So now that we've optimized our material, how are we going to actually build with it? And it's a long way from the laboratory to the building site, and it's a journey that we're still on. How can we build with 2 mixes of different densities at the same time? What sort of formwork is going to be effective? How will composite material dry? How will it deform? Will it crack? And how can we get efficiency of time and cost? The 2-country project team brought different experiences of how to build, of construction processes and industries, and in particular in the use of formwork and materials. And we set about doing some test walls in different methods to try and figure out what is the best way of building with CobBauge here in Normandy using the dense cob mix, and preparing slips and mixing the light earth with different kinds of machinery, and then building test walls with different building formulations of formwork and different methods to make the two different layers. And there's a myriad of different ways you can build a wall like this, and we tried to test as many ways as we could possibly think of. And we built many different walls in many different ways, and we formed different kinds of openings until we came up with really what we thought was the optimal way of building a wall like this. And it's interesting, you can see here that pattern on the surface, which is an open metal mesh, which again takes us back to some of the chats with Scarlett's discussion about innovative use of formwork. That allows the wall to dry immediately. So in the end of the initial 3 years of the project, we had achieved success. We combined two optimized blends to reach thermal and structural standards. We'd shown that light earth and cob can be built in formwork simultaneously to obtain a strong bond. The project won funding for a second phase from the Interreg Fund to construct prototype buildings to enable commercial use. And we're now about halfway through this further 4-year phase. So we're finding that it's a long distance from building a test wall to constructing a whole building. This phase will study how to standardize the materials, construction details, compliance with the regulations, efficiency in the construction process, which will really come down to the key issues about cost and time, and then looking at performance and use and how we can train people to use this technique. So in Normandy, we're currently constructing a small test building, and in the UK, a test wall at the University of Plymouth. I'll quickly run through the construction of the Normandy building. To date, here's the first lift off a concrete plinth. The second lift with the formation of an opening, and here you can see the dense inner layer of cob and then the installation of the light external layer. The next layer, you can see the formwork being lifted up and the use of a digger to speed up construction. And here, the blanked off areas for the openings. Trying different methods of producing the slip to see which is the most efficient, how to lintel over the openings, how to work at height off scaffolding, increasing the formwork and using machinery to lift the materials. The higher levels, and reaching the level of the timber structure for the roof. The top level, which is about where we've got to now, with the final lift due on site soon, weather permitting. And meanwhile, at Plymouth University, we're building walls within the laboratory to test the structural stability and strength of a full-scale component. And now I'm going to show you quickly the work that we've been currently undertaking with another 2 years of the project still to run. So we hope to construct 2 pilot buildings in France and in the UK in the next 18 months, and then monitor them in 2022 with the final results in 2023. We're currently studying the preliminary results from the pilot buildings in France for construction details, differential shrinkage, different techniques and different materials. Some cracking has emerged in some of the areas of stress within the denser cob, and it's important to consider the different traditions between the UK and France in terms of how cob is built. Some initial cracking that's emerged on the external layer of light earth around the lift lines, and we've installed probes into the walls, measuring how they dry out using different drying characteristics and making sure that the light earth within the core of the wall isn't susceptible to rot, and whether there's a way of optimizing that process. So the key issues are what is the optimal degree of moisture in the 2 mixes, the process to avoid differential shrinkage, and what is the most efficient process for people and time and machinery in order to achieve a fast build. We've been measuring the time that it's taken workers on site to build the different lifts in different ways to assess which is the most efficient. And from that, to estimate the cost of constructing a wall in this material, which is the key issue if we're going to deliver the benefits of low carbon construction by having it used widely. And it's fair to say we haven't got there yet in achieving something that's financially competitive with conventional construction, but conventional construction isn't able to compete in terms of environmental performance. And we've only to date been working at small scale. So this is a key area for optimization now, the optimization of the economic design of the material, and there is potentially a role for prefabrication in enabling rapid construction on site. We have also been looking at the construction detailing and how do we add structural loads onto it, the design of the opening, integration of services, foundation and base details, issues around thermal insulation continuity and airtightness, and trying to come up with a range of details that will be published as design guidance. So there are 2 buildings currently in design, one in the north of France and one in the UK, which will be built in the next couple of years and then occupied to test their performance in real life situations. This will test real life, a range of techniques that have been developed in the pilot buildings, method of achieving a sound bond between the 2 materials and a good drying performance. And effective finishes, whether we can achieve a fair face finish, avoiding the cost of a render internally, and the range of external finishes that will both bond to the light earth and be durable in the long term. At the moment, we're overwintering trials of 6 external renders to look at the range of technical performance, cost and environmental impact. These 2 buildings will be monitored for a year post-construction for thermal performance, airtightness and acoustic performance. And during the next 2 years, we'll also be delivering a program of training for contractors and for professionals so that people can design CobBauge buildings with confidence. This training will be developed in line with the ECVET and JUMP European programs, so it can be delivered across Europe to the same standard of skills, knowledge and competence. So if you're interested in this, do visit our website, www.cobbauge.eu, and we're also on Facebook, Instagram and Twitter, where you'll find the ongoing results of the project and get further information as the project progresses. And there you'll find this contact form, which if you fill it out, you'll be sent more information as the project progresses and opportunities to engage in some of the training activities that we'll be having over the next couple of years. And maybe we'll post this into the chat, the link for this page. Thank you very much. I'm now, hopefully, by the miracle of the internet, with somebody else in charge, going to take you seamlessly over to Plymouth University Laboratory.